Okay, so what we talked about last unit was the idea of standing waves. We focused primarily on standing waves of strings and how that was a phenomenon of interference where things were timed up perfectly. And again, for standing waves, what I would see is that wave kind of fluctuating between crest and trough, but things are timed up perfectly where all it does is it appears as if the wave is standing still and not moving forward. And again, you get that altering between crest and trough. And this is, again, sets the foundation for what we just talked about, the idea of harmonics and octaves. That the first standing wave, also known as the first harmonic, would be when I would have, for example, just altering between a crest and a trough. You have two nodes at either ends of the string and an antinode. You would have the same thing when, again, I would add a node in to get to the second harmonic. And then the third harmonic would be the same thing, add an additional node. And what you get are kind of those loops, the fluctuation of those antinodes. But this is the foundation of all sound and music as well. So again, kind of relating everything, if I were to pluck a string, it's going to vibrate at a certain frequency based on that standing wave. So it's going to vibrate at a specific harmonic. And say it's an acoustic guitar. That vibration might then cause the air inside that acoustic guitar to vibrate and resonate at a more intense sound. All right, so what we're going to look at next is the idea of standing waves in air columns. So we looked at the idea of standing waves in strings. So think of that as relating to guitars or a violin or anything that has a string to it. We could produce standing waves in percussion instruments like drums. Now that's a little bit more difficult for us to understand at this point. What we're going to do is look at some of the other types of instruments. So for those of you that know instruments, you have like the brass, which is like the trombone, tuba, things like that. You have the woodwinds, like the clarinet, that have like a reed. And really breaks down into different types. And the physics behind it is all about the air column, okay? So all those types of instruments, take for example a flute. A flute is essentially an air column. What you have here is the hole in which you blow kind of across, called the embouchure, if you will. So you blow air across, and that air vibrates, and that vibration travels all the way down the tube, and what you get is that property of resonance, where you're going to get an intensified sound. And depending on the keys, all it's going to do is change the length of the air column inside, and that's going to create different notes, and essentially what happens is it creates different standing waves. So what we're going to do is we're going to break this down into two types: standing waves and air columns that are open at both ends and ones that are closed at both ends. So for example, a flute would be one where it's open at closed ends. Opened at both ends. Here you have the opening that you would blow across, and then you have the open end there. So what you're getting is a standing wave pattern that occurs between two open ends. Now, the way to think about an open end is that the air particles at those ends are able to vibrate back and forth. They are free to move, which means we're going to treat those, I'll write as AN, as two antinodes, okay? And depending on the key that we might press, we would add different antinodes and nodes inside. So in an open end, what we have is we have an antinode at either end of that air column. Now, what we should hopefully remember from last unit is that between every antinode, I should have a node. So what happens, and what we're going to do, instead of viewing this as a compression and rarefaction, I'm actually going to draw this as a transverse wave so it's easy for us to visualize. So again, think of an antinode as a crest or a trough, so I'll draw it as a crest. The node is that rest position, so if I start from up here, it's going to go down through. Now, it can't go back up, but it's going to go down to the bottom like that. Okay, I could have started from the trough and gone up and through and gone up to there as well. So it could have looked either way, but this is essentially what a standing wave is going to look like inside. Now, we're viewing it as a transverse wave. That's just going to help us to relate it back to what we talked about in our last unit with just regular transverse waves. But the idea is that in each of these columns, between every antinode, you're always going to have a node, okay? So what that's going to produce then is it's going to produce different harmonics and different frequencies at which we're going to create standing waves. So this very first standing wave that I drew, based on the antinodes at either end because of the open ends, this is technically the first harmonic. So in this case, in an open air column, you would have for the first harmonic 2 antinodes at either end and a node in the middle. There's always going to be a node between every antinode, okay? Now again, harmonics occur at specific frequencies, and if you remember, there's that relationship between speed of a wave, frequency, and wavelength. And you can see here, obviously, the wave, if we think about in terms of the wavelength, we have here just the top part and the bottom part. A complete wave would be a total crest plus a total trough. So what I'm seeing here is just the back half of that crest and the front half of that trough. So if I think of how much of a wave I have here, think if I have that chunk, here's my middle, here's that chunk. So what I have here is technically think of this as a fourth, whoopsies, a fourth, a fourth, a fourth, and a fourth. So since I have 2/4, I technically have here half a wavelength, okay? So within that one air column, I have a half a wavelength. So my first harmonic would occur there. So if I were to draw this out again, for my first harmonic, I would have 2 antinodes at either ends, and what I would have then is a node in the middle. So then my first standing wave would go antinode, node, antinode. And again, I'll draw it below so you can see kind of both ends. Now, that's our first standing wave, which again is going to have that within that length, you're going to have a half a wavelength, okay? Now, if I were to draw the next standing wave, again, for an open air column, I'm going to have an antinode, at either end. Now, the way to think about an open air column is that if I want the next standing wave, I'm going to add another antinode in the middle. Now, this is different than we talked about strings, because strings we were adding nodes. Now we're adding antinodes. But between every antinode, there's always going to be a node, okay? So that means my second standing wave would start here. It would go through the node, up to the top to an antinode, back down through the node, and into here. And again, I started from a trough, so if I were to draw the other end, it would look something like this. Now, in terms of this wave, I have here my full crest, and then I have 2/4 here. So within this length, I have 1 full wavelength. Okay. Now, in terms of the harmonics, again, this was the first harmonic. This is the second harmonic. Okay. So we can relate that idea of the number of harmonics to the length. And in this last one, again, I'm going to have my 2 antinodes at either end, but now I'm going to try and squeeze 2 more antinodes inside. I always add an antinode, which means that between every antinode, I'm going to add a node. So this wave, start at the top, would go through, down, then up and through, and like that. Doesn't look the prettiest, but it looks something like this. Now, in terms again of the wavelength, okay, this is a little bit trickier to understand again, but you have here 1 complete wave, and then you have a quarter here and a quarter here. So technically you have 1.5 waves. So within this length, you have 1.5, which I'm going to write as 3/2. Because what we talked about is that within that length of a string, the relationship between the harmonic and the wavelength would be n/2 times whatever that wavelength is. Again, that's going to tell you the harmonic. And again, this last one I forgot to write down would be our third harmonic. Okay, so this would be the relationship we can look at between the length of that open air column, I think I just said string, and the wavelength that we would have. And again, each of these would occur at different frequencies. So this looks a little bit different than what we talked about last time because we're not starting with 2 nodes, we're starting with 2 antinodes. All right, now we're going to go through some examples. The first one we're going to do is identify the harmonic. And all this is I like to do it as counting loops, okay? This is kind of the best way to do it. So when we count a loop, think of a loop as, when we looked at last unit, a node to node with an antinode in the middle, okay? Now, for the first harmonic, we should have 1 loop. For the second harmonic, we should have 2 loops, and so on, okay? So if we were to identify these patterns, notice here how we don't have nodes at either ends, but we have antinodes. But if we think about the amount of a loop, I want you to notice that this is technically half a loop, and the other side is also half a loop. Well, 2 halves means that technically we have 1 loop, which means that this right here would be the first harmonic. okay? If I were to continue, I have here a half plus 1 plus a half. So let me just write this out. So a half plus 1 plus a half. Well, that would give me 2 complete loops, even though I can't see it, which means this would be technically the second harmonic. So if I were to continue this trend, I'll just do one more for you guys. Half, 1, 2, another half, so I have 2 in the middle and then 2 halves. So this would technically be the third harmonic, and this would be the 4th, 5th, 6th, and we can continue on to whatever harmonic we look at. So you have your complete loops again. So again, you count the complete loops that you have, and then you have 2 half loops at the end. In total, they have to add up to whatever harmonic we're at. So in terms of the frequency, we can just simply identify it based on the loops. Now, another trick that also people like to look at is, this kind of relates back to what we talked about in our last unit, is that when we look at the specific harmonic, that the number of nodes also represents which harmonic we're on. So you notice the first harmonic has 1 node, second harmonic has 2 nodes, then we have 3 nodes, and 4 nodes, and so on and so on. So this is a way in which we can then recognize it based on the frequency. So for example, if I have here a frequency of 80 hertz, I want to highlight that, and let's say that that's the fundamental frequency. That's the first standing wave, which in a open-end air column would look something like this. Again, it's going to be 2 antinodes at either end with a node in the middle. So what we have here is we're going to draw the wave pattern for a frequency of 400 hertz. And I want to identify which standing wave pattern would that be. Okay, so the standing wave pattern, again, is going to be based upon the frequencies. So if I have here a frequency of 400 hertz, compare that to the original fundamental frequency of 80 hertz, divide those two out, you would get 5, which means we're going to be on the 5th standing wave. So the 5th standing wave means we're going to have 4 loops and then 2 half loops at either ends. So again, we're always going to have our 2 antinodes at either end. Okay, so an antinode here and here. And then we need nodes in the middle. Now, what we talked about in the previous slide is that the number of nodes is going to equal the harmonic we're at. So if I'm on the 5th harmonic, that means that within this air column, I want 1, 2, 3, 4, 5 nodes. And then again, between every node, you have an antinode. So I'd have an antinode, 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 and then this one should be down there, not up top. Okay, so if I were to draw this out for you guys, I would start from my antinode, which is the open end, go through, and then I'm going to fluctuate up and down, again, through there. And again, I could start from the bottom, but you would see it looking like that. So in terms of, again, the loops, I would have 1, 2, 3, 4 loops, and then 2 half loops at either end for my 5th harmonic. All right, our next example, there's a little typo, folks. It does say 60 here. This I wanted to change, forgot about that. We're going to change that to 100 hertz. But again, we're going to compare the fundamental frequency of that air column to its new frequency for that standing wave pattern. So here we have the fundamental frequency of 100 hertz. That's that first standing wave. And I want to know, what does the standing wave pattern look like at 300 hertz? So if I just take 300 and divide it out by 100, I'm going to get 3, which means I have the 3rd harmonic. Any standing wave in an open air column is always going to have 2 antinodes at either end. And again, it could be a crest or a trough, or a compression and rarefaction, I should say, which means then we're going to have nodes in the middle. Because we're on the 3rd harmonic, we should always have an equal number of nodes to the harmonic we're at. All right, which means I'm going to go from antinode through the node down here, then back up, then down, and then to there. Okay, so again, I need an antinode between every node that I would have. And again, if I were to draw it the opposite direction, I have that. So in counting loops again, I would have 1 loop, 2 loop, and then 2 halves at the end for a total of 3 loops. So this again is just identifying what the wave pattern looks like based on its frequency. All right, this last one, we're going to look at the relationship between the wavelength and the length of the string to identify the standing wave pattern. This one is a little bit trickier to understand again. And what we looked at is that within the length of string, it always had the relationship of n over 2 times the wavelength, where n represents the harmonic we're at. So to kind of understand the harmonic, what we're going to do is look at the relationship we did last unit, I should say, where the harmonic we're at is going to follow this relationship. It's always 2 times the length divided by our wavelength. Okay, so this is the relationship we're going to use if we want to relate it to the harmonic based on the length and the wavelength. So for example, in this one, we have a length of the air column, which is 48 centimeters, and the wavelength is 96. So what I'm going to do is I'm going to take 2 times the length, which is 48, and I'm going to divide it by the wavelength, which is 96. So 2 times 48 would give you 96. Divide that by 96, you get 1. That means when we get 1, we should see the first harmonic. So the first harmonic, again, open air column, we're going to have an antinode at either end, and we're going to have 1 node in the middle. So if I were to start from, let's say, a crest, I would go through that node and then to a trough. And again, if I were to start here from a trough, go through the node up to a crest. So that would be my first standing wave. Second example here, again, I'm going to look at my length of 48, my wavelength of 24. So if I want to find the harmonic, I'm going to take 2 times the length, so 2 times 48 again, and now compare that to the wavelength 24. So 2 times 48 again is 96. Divide that by 24, and you're going to get 4. So that means we have the 4th harmonic. Now what does that look like again? This is the difficult thing in drawing, is I would have 2 antinodes at either end. Oops. And then the number of nodes is always going to be equal to whatever harmonic we're at. So I would have 4 nodes. So between every node, and this might help to draw it out, let's say I start up top, I would go down to here. I would need an antinode in between and then back up through. I need an antinode in between, go back down, antinode back up to my antinode. Okay, and I'm at the end. That one didn't look as pretty, but I'll try and draw it nice and smooth. Look something like that. And again, to count the number of loops, I have 1 loop, 2 loop, 3 loop, and then my 2 halves would give me 4 loops. So that is for an open air column, looking at the pattern based on the frequency and the wavelength. All right, last thing here, folks. I know we're getting a little lengthy here, but this is the last meat and potatoes. So we looked at open air column. For those of you that play instruments, you might play something like a woodwind instrument, or that maybe requires the use, instead of an embouchure, might use what's called a reed, where, a reed is technically a closed end. But even though it's a closed end, we still over here have an open end. So you might have, instead of 2 open ends, you might have a closed end and an open end within an air column. The only difference between this is that instead of having 2 antinodes, here you would have a node at the closed end and an antinode at the open end. So in terms of my air column, I would have node here and antinode. Now the tricky part about this is that you always want a node followed by an antinode. So here, there would not be an antinode in between them, nor would there be a node in between them. So my wave would start at the rest position and go to a displacement. So it would look something like whoop. Or if I drop below, something like whoop, like that. Now the tricky part about this is that if I think of a complete wave and think of that rest position, all I have right now is from a node to an antinode. So I only have this chunk of the wave. So understand, being shown right here is only a quarter of the wave. So within this length of tube, I have a quarter of the wavelength. All right, now this first one where I have a node and an antinode, this is technically the very first harmonic. If that's the first standing wave I can draw, that's the first harmonic. So again, the relationship is that within that length of string, I would have 1/4 of the wavelength. Like how I used that little mark there to represent a 1. That was pretty neat. Okay, again, that is because I had node and an antinode. Now, for every other standing wave, and again, this is going to look at the harmonics, I'm always going to have a node at the closed end and an antinode at the open end. When I want to draw the next standing wave, I'm going to fit a node in here as well as another antinode. Okay? And the way this would look is go from node to antinode to node to antinode. Same thing if I were to go down to an antinode, through the node, and then up to that point there. Now again, what we're going to try and do is represent what or how much of a wave that we have at this specific frequency. And again, this is occurring at a certain frequency. So to compare this to the diagram down here, notice I had, first of all, my first one I had a quarter wave, but now here I have a loop plus all the way down to an antinode. So I would have the entire loop plus down to an antinode. So I would have this much of the wave from there. So if I count this, think of this again as quarters. So I would have 1/4, so 1/4, another fourth, and another fourths. So what I have here is technically within this length of tube is I have 3/4 of a wavelength. Now on the next standing wave, again, if I were to follow this pattern, node, and at the end I would have an antinode. If I want to do the next standing wave, I now have to go from one node in the middle to now 2 nodes. So I gotta have 2 nodes within that tube, again, not counting that one that's automatically at the end. So that means I would need antinode in between. So I would have to go up to the antinode, through the node, then back down to the antinode, then through the node, and back up to the antinode. And the same thing here, it'd be down, up, and through, and it looks something like that. So if I were to count waves here, notice that I have up and down, so that's a complete wave, plus that quarter. So I have one complete wave and then a quarter. So to kind of relate that to fourths, I have one complete wave would be 4/4, plus a fourth would give me 5/4. So I have here 5/4 of the wavelength. Now what's interesting about these closed-end air columns is the pattern it follows. Notice here that I go from node to antinode. I have 1/4 of a wavelength. Then I go right away to 3/4 of a wavelength. Well, what happened to, think about 1/4 to 3/4, what happened to the halves? Right? What happened to half a wavelength? What happened to a full wavelength? Notice I'm skipping those even numbers. And that is because in a closed air column, you do not have the even harmonics. This is the first harmonic, okay, the fundamental, if you will. This is technically the third harmonic, and then this is the fifth harmonic. So for a closed end air column, you will only have the odd number harmonics. We actually skip the even number harmonics, and that's what makes these a little bit different. Okay, so in terms of the types of sounds we can create from this instrument, we don't have the flexibility that we would have from an open-end air column. Okay, so now what we're going to do in our first example, like before, is identify the harmonic. Okay, so just know that in an air column where you're closed at one end, you have a node at one end where it's closed. You're always going to have your node. Okay, so notice all of these waves start off with nodes. Fantastic. But at the opposite end, you're going to need an antinode. Okay, so because here we have 1/4 of a wave, this is technically going to be the first harmonic. Now the second one, notice I go here. This is kind of what I was talking about. I go from node, antinode, node. Well, here's the thing. Because this is an open end, this has to be an antinode. So this cannot happen. Now this is technically a half a wave. So this would be the second harmonic, but this is not a thing. So the second harmonic does not exist in a column closed at one end. Again, to follow the pattern, this would be the third harmonic. And notice we have our antinode at one end. All right. Next one, we have here a node, but notice we have a node at the open end. That cannot be possible. So our fourth harmonic does not exist. Continuing on, this would be our fifth harmonic. And then this last one, notice this actually works. I have my node here and I have an antinode all the way over here. So how do I identify which harmonic this is going to be? The way I like to do this is to count fourths. Okay, so a whole wave would be crest plus trough. So if I were to cut this wave into a fourth, all right, this would be my half a wave. So if I cut that half in half, a fourth would look like this. So it's going to look from a node to an antinode. So from a node to an antinode represents a fourth of a wave. Okay, so if I were to count, I'll go on this last wave here. I would go from 1 up to here. So I'll just mark these. That's a fourth, 2/4, 3/4, 4/4, 5/4, 6/4, 7/4. So because this is 7/4, that number 7 is going to tell me which harmonic we are on. So this would represent, technically, the 7th harmonic. A little bit sassier with these closed air columns. All right, in this next example, we're going to again relate the frequency here. Okay. Now it's going to be the same kind of thing we did before. You have your fundamental frequency, which is 100 hertz, your new frequency, which is 500 hertz. So we're going to compare these. But again, you're only going to see here odd number frequencies. So we have 500 divided by 100 would give me 5. That means we have the 5th harmonic. So I'm sorry, odd number harmonics. So again, to draw this out or identify, I would have my node naturally at the closed end, my antinode at the open end, and what I need is 5/4. So I'll start from my node. I would go up from node to antinode. That's 1/4. Back to node, 2/4. Antinode, 3/4. Node, 4/4. Antinode, 5/4. So if I were to draw this out, it would go up, down, and through, and there. So I got to count the fourths. And if I were to draw the other way, it would look something like this. So that would be my 5th harmonic, okay, counting fourths of a wave. All right, now last example, baby shawties, but what we've been looking at again is that relationship between, the nodes and antinodes and which harmonic we're at. So how do we relate this to length and wavelength that we've talked about? So we've been looking at the idea of fourths. So you have n/4 times whatever the wavelength is. But no, in this case, that n can only be odd numbers. So 1, 3, 5, 7, and so on and so on. Now, because we're cutting things in the fourths, and how this is different from an open air column, is that if I want to find the harmonic we're at, we're not going to double the length, but we're going to do 4 times the length divided by the wavelength. So this is the equation or relationship we'd use to find the harmonic we're at. So in this case, if my length is 48 centimeters and my wavelength is 96, I would do 4 times 48 and divide whatever that is by 96. So multiplying 4 times 48, I would get 192. Divide that by 96, I'm going to get 2, which means this should be the 2nd harmonic. Now the 2nd harmonic, when we have a node at one end and an antinode at the other, again, we talked about that this would only occur at an odd number. So is it possible to have a 2nd harmonic? So understand that this is not possible. Now to draw it for you why it wouldn't be possible is that if it is the 2nd harmonic, okay, 2nd harmonic means that we need 2/4. 2/4, same thing as saying half a wave. So a half a wave would look something like this, okay? Draw it there, boom. Now why this is not possible is because when I draw a half a wave, notice at this end I have a node. And because it's an open end, that is not a thing. That is not possible. Okay? So this is what it would look like, although it's not possible to have that 2nd harmonic. All right, a lot of meat and potatoes. I apologize for the longer video, but a lot of interesting things when we look at sound interference. Okay, good luck on those concept builders, and we'll see you next time, folks.